Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on mixing and solutions. In the last lecture, we looked at the fundamentals associated with mixing and solutions, and we performed some simple energy balance calculations where we had to account for mixing and formation of solutions as a part of the energy balances that were being done. Today we will perform a couple of more problems. So this would be a tutorial session where we will look at two problems which I will try to explain step by step, and this will help you understand how we would go about performing these calculations. So here is the first problem. The first problem states that water is added to pure sulfuric acid in a well insulated flask initially at 25 degrees Celsius and 1 atmosphere to produce 1 liter of 4 molar sulfuric acid solution. The specific gravity is given as 1.231. The final temperature is to be 25 degrees Celsius, so that the water added must be chilled liquid at temperature much less than 25 degrees Celsius, or a mixture of liquid water and ice. What are the masses of water and sulfuric acid that need to be mixed? Assuming only liquid water is added, calculate the initial temperature of water required. Is this process feasible? If a mixture of liquid water and ice is added, how many grams of liquid water and how many grams of ice need to be added? You have been given that Cp of ice can be used as half of that of liquid water, and delta Hs cap, which is the heat of solution for preparing 4 molar sulfuric acid solution, is given as minus 67.6 kilojoules per mole of H2SO4 dissolved in the solution. So we have all this information. So let us see how we can go about solving this problem. So the first information which we are looking to find is the masses of water and sulfuric acid. So this is a simple material balance calculation that can be performed if we know the definition for molarity. We have been given that the solution which is given to us is 4 molar sulfuric acid. This means that 4 moles of H2SO4 is present in 1 liter of H2SO4 aqueous solution. So this is what 4 molar means. So let us look at what is the molecular weight for sulfuric acid. So molecular weight of H2SO4 is equal to 98.1 grams per mole, and this molecular weight would imply that 4 moles of sulfuric acid present in 1 liter means that 4 times 98.1 grams of sulfuric acid has to be dissolved in 1 liter of solution. So our basis for the problem is 1 liter of 4 molar solution being prepared. So this means 4 times 98.1 grams of sulfuric acid is dissolved. This would be 392.4 grams of sulfuric acid dissolved in 1 liter of solution. So you need to use 392.4 grams of sulfuric acid, and in the 1 liter solution it would be sulfuric acid and water that are present. So we know that the mass of sulfuric acid is 392.4 grams of sulfuric acid. So what is the mass of water? So we know the volume of the solution and we know the specific gravity of the solution. So we can calculate the mass of the solution. So mass of 1 liter solution would be equal to 1 times 10 power 3 times 1.231, which equals 1231 grams. So 1 liter of H2SO4 solution, 4 molar H2SO4 solution would weigh 1231 grams. So this implies mass of water would be equal to 1231 minus 392.4 grams, which would be equal to 838.6 grams of water. So, you can prepare 4 molar H2SO4 solution, 1 liter of it, by mixing 392.4 grams of sulfuric acid and 838.6 grams of water. So, for the next part of the problem, we have been asked to calculate at what temperature this liquid water must be if it has to be mixed with sulfuric acid, so that the final temperature will be 25 degrees Celsius. So, how do we go about doing this? So, we have to assume that liquid water at temperature T is being mixed with sulfuric acid, which is initially at 25 degrees Celsius. We want the final condition to also be 25 degrees Celsius, which means that you are going to have water less than 25 degrees Celsius added, because there is going to be heat generated while the solution is being formed. Therefore, for this to maintain at 25 degrees Celsius, the water added would have to be at a temperature which is significantly lower than 25 degrees Celsius. Let us see how we would do this calculation. So, the components which would be present in this system would be water liquid and sulfuric acid liquid. Those two will be mixed to form sulfuric acid aqueous, which would be the final condition. So, we need to identify reference states for these components. So, for any time we have a solution, what we have looked at is we could use the reference state as the pure components. So, that is what we would do. So, here we will take the reference states as water liquid at 25 degrees Celsius and 1 atmosphere, and sulfuric acid again a liquid at 25 degrees Celsius. So, these are the pure components which are being taken as the reference states. So, let us look at the number of moles of water and sulfuric acid which have to be supplied. So, we will have to write this in terms of moles, because the enthalpy terms are given in terms of kilojoules per mole. So, we will write the number of moles of water and sulfuric acid which is being present initially and finally. So, you have N in and H cap in, N out and H cap out. So, we know the mass of water which is being supplied, which is 838.6. So, converting this to moles, it would be roughly 46.57. So, you just divide it by molecular weight. We know that 4 moles of sulfuric acid is present in 1 liter of the solution, that is why it is a 4 molar solution. So, H2SO4 is 4 moles. So, and the final condition, you do not have any liquid H2O and liquid H2SO4 present, you only have aqueous H2SO4. So, there is no initial aqueous H2SO4 entering into the solution, the final condition or the outlet only has H2SO4 solution. So, what would be the number of moles that we write here? If you look at the data given for heat of solution, it is given as kilojoules per mole of H2SO4. So, we should write the number of moles of H2SO4 present in the aqueous solution, not the total number of moles of the aqueous solution present. So, this means you would write 4 as the number of moles of H2SO4 present, and this should be multiplied with the enthalpy data to get the total change in enthalpy. The specific enthalpy times this will give you the total change in enthalpy. So, now what are the enthalpy values for this? So, you have H2SO4 liquid which is present at 25 degrees Celsius and 1 atmosphere, which is the same as the reference state. Therefore, this enthalpy would be, specific enthalpy would be 0. You have water liquid which would be coming in at a temperature T, and the reference temperature here you have is 25 degrees Celsius. So, this would mean that this value you have for water, which is the reference, so the value, enthalpy value you have for water would be H1 cap, which needs to be calculated, and similarly there would be an enthalpy for aqueous solution of H2SO4, which would depend on the heat of solution. So, let us say that is H2 cap, and the other parameters do not have to be accounted for. So, now for H1 cap, what is the process? Water liquid at 25 degrees Celsius, which is the reference state, goes to water liquid at temperature T. So, we have been told that in the first part that we will be using only liquid water. So, the liquid water would have to be at a temperature T for the cooling to happen. So, for this process, your H1 cap would be equal to integral Cp dt, where temperature changes from 25 to T. So, if we were to use the Cp value in terms of kilojoules per mole degree Celsius, then the units the value for Cp is 0.0754. So, you can convert the Cp in terms of joules per gram degree Celsius, which is roughly 4.18 to the units of kilojoules per mole degree Celsius, and check whether the value I have used is correct. So, you have 0.0754 times T minus 25, which is H1 cap. H2 cap is for what process? You have pure components becoming the solution. The solution is at 25 degrees Celsius. So, this means the standard heat of solution which is obtained, or the heat of mixing which is given in the problem, can directly be used. So, this would mean you can use that value, which is H2 cap would be equal to the delta Hs cap which has been given, that is minus 67.6 kilojoules per mole of H2SO4. So, substituting these values here, we would have H1 cap as 0.0754 times T minus 25, and H2 cap would be minus 67.6. So, now with this we can start calculating the delta H cap. We have been told that the system is perfectly insulated. This means it is it is basically a process where there is no heat being transferred from the surroundings or to the surroundings. So, your Q would be equal to 0. So, the equation actually would be Q equals delta H, which would be equal to 0, because we do not have any shaft work or change in kinetic and potential energies. So, you would end up with delta H equals 0. So, the delta H can be calculated as 4 times minus 67.6 minus 46.57 times 0.054 times T minus 25 equals 0. So, from here we can calculate the value for T. So, T would be calculated as minus 52 degrees Celsius. So, this means that liquid water at minus 52 degrees Celsius needs to be fed for the temperature of the final aqueous solution of H2SO4 to be 25 degrees Celsius. In other words, this is not possible. You would not have liquid water at minus 52 degrees Celsius and 1 atmosphere, it would be a solid. So, this means we cannot use pure liquid water for the process to continue. So, not possible. So, this is not possible. So, now we need to look at what other alternatives are there. Third part of the problem asks us to find what if we used solid liquid mixture. So, ice water mixture. So, if we were to use ice water mixture, then what you would have is ice would have to melt and temperature would have to change. So, therefore, there will be an effect because of this, and therefore, we might have to identify how much of ice and water has to be present. So, we will be able to get the 25 degrees Celsius. How do we go about doing that? Again, we will only have two chemical components, which are water and sulfuric acid. So, we need to identify the reference states, considering that we still have to use the heat of solution given in the problem, which is the standard heat of solution. We would use pure components at 25 degrees Celsius as the reference state, water liquid at 25 degrees Celsius and sulfuric acid liquid at 25 degrees Celsius would be our reference states. Now, what are the substances or components present in the system now? we said that we will have water liquid and water solid come in as a mixture. So, we would have water H2O liquid and H2O solid, both that need to be accounted for in the specific enthalpy table. You would have H2SO4 liquid and H2SO4 aqueous also in the system. So, now again we will write N in, H cap in, N out and H cap out. So, for N in, let us say it is NL for the amount of liquid water and NS for the amount of solid water or ice, because we do not, that is what we need to calculate. We need to find the mass of liquid water and solid ice for the final answer. So, we will take them as two variables. We know that 4 moles of sulfuric acid is present in the 4 molar solution, which is of 1 liter. So, this value is available to us. So, and we do not have any aqueous sulfuric acid coming in, but we have sulfuric acid leaving as aqueous solution, and we will again write only 4 moles. As I already mentioned, we will be using the enthalpy of solution, heat of solution, which is given as kilojoules per mole of H2SO4. So, we will only write the number of moles of H2SO4 here. There is no liquid water, solid water or sulfuric acid liquid as pure component leaving the system. So, what are the enthalpies? Which enthalpies do we have to calculate? So, enthalpy of water has to be calculated because it is not coming in at 25 degrees Celsius. Similarly, enthalpy of ice also has to be calculated. Enthalpy of liquid sulfuric acid would be 0 because it is present at 25 degrees Celsius, and which is the reference state which we are using, and this we do not have to worry about. These 3 we do not have to worry about, and we have to identify the enthalpy associated with the formation of sulfuric acid aqueous. Now, these are the terms which we have to identify. In the last part of the problem, we were trying to identify the temperature. Here we have not been explicitly given the temperature. So, what temperature do you think we would use? We have water and ice coexisting. This means the temperature would have to be 0 degrees Celsius. Because it is 1 atmosphere, water and ice will coexist at 0 degrees Celsius, and we will use that for performing the calculations. So, for H1 cap, we basically have a process where water from the reference state, which is water liquid at 25 degrees Celsius, becomes water liquid at 0 degrees Celsius. So, all we have to do is identify this process and we will be able to calculate the enthalpy. So, here it is only delta T which is happening. So, all we need to do is integral Cp dt, where temperature changes from 25 to 0. We already know the Cp for water. So, for H1 cap would be equal to 0.0754 times 0 minus 25. This would be in terms of kilojoules per mole. Now, let us calculate H2 cap. So, what is the process for H2 cap? You have water liquid at 25 degrees Celsius, which is the reference state, going to water solid at 0 degrees Celsius. So, now this actually has 2 steps, where water liquid at 25 degrees Celsius is cooled to water liquid at 0 degrees Celsius, and from here it solidifies to form water solid at 0 degrees Celsius. So, these 2 steps are there, one where there is change in temperature and the other where there is change in phase. Now, let us see how the total change in enthalpy, which is H2 cap, can be calculated. H2 cap would be, for the first step, it is integral Cp dt from 25 to 0 plus delta heat of fusion, but here it is the solidification, not melting. So, you would have the negative of it. So, you can use the standard heat of fusion and get this value. So, this would mean It is integral 25 to 0 0.0754 dt minus 6.01, which is the heat of melting for water at 0 degree Celsius. You can look it up from any table available in your textbook or handbook. So, this value can be calculated. So, H2 cap can be calculated from here and H1 cap can be calculated from here. Now that we have H2 cap and H1 cap, we can revisit the table. So, from the specific enthalpy table, so delta H would be equal to 4 times minus 67.61 minus NL times H1 cap minus NS times H2 cap. So, this is what we have. Now, we have already calculated H1 cap and H2 cap, we need to calculate NL and NS. So, we already know the number of moles of water which needs to be fed. We know the mass is around 838.6 grams. So, this would mean that the number of moles would be 46.57. So, implying NL plus NS is equal to 46.57. So, now this can be substituted back into the equation we have for delta H, and we know that delta H equals 0 because Q is 0 for this process and there is no change in kinetic energy, potential energy or shaft work. So, using this equation we would end up having 4 times minus 67.61 minus NL times minus 1.885 minus 46.57 minus NL times minus 7.895 equals 0. So, from here we can calculate NL as 16.18 moles of water and therefore, NS would be equal to 30.39 moles of ice. So, mass of liquid water would be 291.4 grams of water and mass of ice would be 547.3 grams of ice. So, both would be at 0 degree Celsius. So, this is what we would have, and if we were to add this masses to the H2SO4 solution, 4 moles of H2SO4 at 25 degrees Celsius, and we have a process where there is no heat being transferred, we would finally end up with 25 degrees Celsius temperature for a 4 molar H2SO4 aqueous solution. Let us move on to the next problem.